Okay, I think we're ready to move towards our next topic, which is an example of a new hypothesis test. But before we do this, I just want to point out how much great work we've done so far. And what I mean by this, and you'll sort of see it reflected as we introduce our new hypothesis test, is you've kind of done the majority of the learning you need to do in order to start understanding other types of hypothesis tests. Now, specifically, we've covered what I would call one sample hypothesis tests. These are claims about a single population parameter. So it's either a claim about a mean or it's a claim about a population proportion. You might call the claim about a mean a one sample t-test because we use our t-distribution to model that null sampling distribution. And you might call the claim about our population proportion a one sample z-test because we use our standard normal distribution to model that null sampling distribution. But keep in mind the steps are pretty much always the same, right? We assume H0 is true, right? If we're trying to answer a claim about mu, we focus in on the statistic that's associated to it. So this is at the population level, and it gets associated with a sample mean, an x bar. So assuming H0 is true, we develop what we call a sampling distribution. Oops. For what x bar would look like, right? Where would our sample means likely fall based on the assumption that our null hypothesis or the claim about our population parameter is true? Once we have that, we use this to compute a p-value. And once we know our p-value, we compare that against our significance value to determine whether or not we reject or fail to reject our null hypothesis. This general process is going to be the same for any hypothesis test that you run. In fact, I can very easily sub out a mu proportion with a mu parameter with a proportion parameter. And the only real change here is that I'm no longer dealing with a sample mean, but now I'm dealing with a sample percentage. And I'm no longer interested in the distribution of sample means, but I'm interested in the distribution of sample percentages. And if I have a good probability model for this, this means that my p-value, I can compute my p-value based on the sample I actually do observe, and then so on and so forth. So you can envision sort of other parameters that you might want to work with. We won't go over this particular example, but here's another parameter that you're familiar with, a population standard deviation. Its sample version is just a sample standard deviation, S. And we can think about what the probability or what the sampling distribution for sample standard deviation might look like. It turns out it doesn't have a t or a z distribution associated to it, so it looks very different. But fundamentally, the general process of a hypothesis test will still work. Okay? So we're going to see this reflected in one more example. We're going to talk about comparing means between two different populations. Who's taller, men versus women? Okay? And we're going to talk about this general process, and I'm going to show you a quick and easy way to get this p-value just by using an Excel command. So again, part of the point of going over this new hypothesis test is to show you that the process that you've learned on these one sample hypotheses tests is perfectly reflected in other types of hypothesis tests you may want to consider as you learn more about statistics and do more complicated studies. There are many other hypothesis tests we could use or we could test using statistics. So here's just a little bit of a setup to show you what I mean by this. I could hypothesize that maybe the mean weights of Labrador retrievers are the same as the mean weights for Chihuahuas. Okay, so if I look at the population of labs and the population of Chihuahuas, my claim is that the average, the mean in the population, is the same for both. Now, obviously, this isn't true, right? Anyone who's seen a Chihuahua and anyone who's seen a Labrador Retriever knows that these are very different sized dogs. Their mean weights in the population should be different. But how do I actually show this? Well, same basic type of setup. You take a sample from each population. So I'm going to sample 50 Labrador retrievers, and I'm going to compute some sample statistics. If I'm interested in differences between the population means, I'm going to look at sample means. So my 50 Labrador retrievers had a mean weight of 71 pounds. A sample of 55 Chihuahuas maybe had a mean weight of 5 pounds. Now the idea here is that if these mean weights for the samples are different enough, that provides evidence against my claim that the mean weights in the population are in fact the same. So you can see the structure of the hypothesis test that we've been working with last week reflected in this new approach for a very different type of hypothesis. Now I'm looking at population means for two different populations. So our approach will be as follows. If I assume my hypothesis is true, what is the probability? What's the likelihood of getting the results like the ones that I found in my sample data? And we're going to be able to develop a probability distribution that models this null hypothesis when it's true. And then we'll use our sample data to, with that probability distribution, to compute a p-value. Based on whether that p-value is above or below our significance level, we'll be able to reject or fail to reject my claim. Now, as I mentioned, there are many types of hypothesis tests. You may have heard of some of them. The ones we've already covered are one sample tests for means, population means, and population proportions. The one we're about to cover is a two sample test for comparing means between two different populations. There's a test called a paired sample, there's a test called an ANOVA, there's a chi-squared test, and there are even hypothesis tests associated to linear regression, which we'll cover in our final topic of the year. But for today, this is what we'll cover in this particular class. You'll have one sample test, the two sample for comparing means, and then a linear regression test. For today, though, I really want to just focus on this two sample test for comparing means of two different populations. So our new hypothesis test that we're going to consider is what we'll call a two-sample t-test for comparing means. And it's fundamentally used to test claims where we're claiming that there's a difference in means between two different populations. Here are a couple of example research questions that we can answer using this type of hypothesis test. Is the mean weight of Labrador retrievers greater than the mean weight for Basset hounds? For an anatomy and physiology exam, is the mean score for nursing majors different than the mean score for exercise majors? Suppose we ask men and women to solve an impossible puzzle. On average, do men spend less time focused on the task than women do? Right, these are all great research questions that we can actually test using our hypothesis test, the two-sample t-test for comparing means. The idea is we think about, for each one, two different populations. For example, in the first one, Labrador Retrievers is my first population, and Basset Hounds is my second population. And I think about randomly selecting a sample from each one of these populations. And in doing so, I can compare their sample means and see if they're different enough to warrant a conclusion that the mean weights in the population are in fact different. So that's going to be our fundamental approach. Let's consider a heuristic example just to get our feet wet here. Suppose we collected all the height measurements for women and men in the United States. Now, if we separate this out, we just consider the men, we might get a population level histogram that kind of looks like this, right? Most men are about 5'8", so we kind of see the highest bar here at about 68 inches. And we have, some that are shorter, some that are taller. We can also separate out the women, and in this case, we would see, again, this is sort of a normally distributed population here, right? It's got unimodal, kind of is symmetric, dies off on either side. However, the peak is a little bit lower. Now we can overlay the two of them, and in this case, the purple region here represents sort of an overlap between the red histogram and the blue histogram. And this is indicating, of course, that, there's some men and women who are roughly the same size. So we do get some overlap between these two height distributions. Now, what we're fundamentally looking for when we compare two populations is a comparison of their population means. Now, when you're dealing with normally distributed data or, nice bell-shaped unimodal data, the mean is roughly the same thing as the highest peak when you're looking at the histogram. All right, so in this case, it's saying, is there a difference between the peaks? More generally speaking, for measurements that are not normally distributed, remember this is the balance point for that population level histogram. But fundamentally, what we're trying to test is if we had all the information, all the population histogram information, and we looked at the means, the balance points for those histograms, would they be different when we separate out by the population of men and the population of women? Right? In this case, we can see visually clearly, yes, they are. But how do you test that if you don't have all the population data? Right? How do you test that just by going off of samples? So how can we detect a difference in means at the population level by looking at a difference in means at the sample level? That's what this two-sample t-test is going to help us do.